I'm Borche Jovanovski, and I'm a PhD student and research associate at the Faculty of Electrical Engineering and Information Technology in Skopje, Macedonia. Today, I'm talking about federated learning for activity recognition. This presentation, I will start with short introduction. Then I will talk about artificial neural networks and federated learning implementation. In the third part, I will talk about the experimental setup. Then I am present the performance analysis and results. And finally, at the end, I will talk about the I will repeat the key remarks from this presentation. Efficiency and effectiveness are important requirements for Internet of Things devices. The ability to process and analyze large amount of data generated by this device in a timely and accurate manner is crucial for their effective functioning. Machine learning has a powerful tool for processing and analyzing big data. It enables IoT devices to learn and adapt based on data they collect, which can lead to more efficient and effective decision making. Federated learning is an approach to machine learning that allows models to be trained on a data set located in different locations without sharing training data. This is achieved by allowing personal data to remain on local sites and reducing the possibility of branch. Federated learning is a centralized server-first approach that enables the collection of data from different sources and location while maintaining privacy and security. Together, federated learning and machine learning together have the potential to significantly improve privacy and online real-time learning with huge data set. When we talk about the federated learning, I will talk about the federated learning is particularly well suited for wearable sensor technology because it enables that device to train model collectively while preserving the privacy of the data. The real-time data collected by these sensors, the real-time data collected by these devices can be used to train machine learning models that can be applied in a variety of domains such as healthcare, fitness, entertainment, and more. Federated learning enables these models to be trained collaboratively, allowing for the sharing of knowledge between devices without compromising privacy. One of the key benefits of FL is that it reduces the need for large amounts of data to be transferred to a centralized server for processing. This can be significantly reduce the communication and processing costs associated with this wearable sensor technology devices, which have limited processing power and energy. The combination of wearable sensor technology and federated learning has the potential to revolutionize a variety of industry, enabling real-time monitoring, personalized recommendations, and predictive analytics, all while preserving the privacy of the user data. Artificial neural networks are indeed inspired by the way neurons in the human brain work. This type of networks are designed to process information through a network of interconnected nodes, also known as neurons. These neurons are arranged in layers and communicate with each other through series of connections that are weighted. There are various types of artificial neural network, including feed-forward neural networks, recurrent neural networks, and convolutional neural networks. Feed-forward neural networks are the simplest type of neural network, where the information flows only in one direction, which is used to solve flows in one direction from the input layer to the output layer. The simplest form of artificial neural networks is the single layer perceptron, which is used to solve linear separable problems. On the other side, in multi-layer perceptrons, the process of updating weights is performed using a technique called backpropagation. This technique is a supervised learning algorithm that adjusts the weights of the connections between neurons to minimize differences between the predicted output and the actual output. On this picture, we will see the federated learning system architecture. The core idea of the federated learning is training shared model using clients that never have to share data between themselves or with a server. The setup of federated learning involves a server and multiple clients that hold their own local data and models. The server initiates the training process by sending the initial model to the clients. The clients then perform local training on their own data and share only the model updates or weights with the server. The server then aggregates these updates or weights to create a new shared model, which is sent back to the clients for the next round of training. The process is repeated until the model convergence or achieve the satisfactory performance. About the experiential setup, for the purpose of training and and evaluation of the model. In my work, I use the JSI phone dataset. This dataset consists recordings collected from 10 subjects. From 10 subjects, while performing the following activities of daily living. Each user's recordings consist of data from inertial sensors, which users were attached to different parts of their bodies in the form of inertial measurements units. In this analysis, we considered only the data collected by this instrument placed on the wrist of the dominant hand and tight of the dominant leg, and only consider data coming from the accelerometer and gyroscope. After that, we will have some metrics. This is the F-score matrix, which is defined as the harmonic mean of the precision and recall matrix for a particular label. This matrix allows avoiding the bias of metrics such as the accuracy of activity with a large number of examples by calculating the F-score for each activity separately and reporting the average of the results obtained. The architecture of feed-forward neural networks is shown in this picture. It consists of an output layer which has many neurons as their feature that describe a single window of data, followed by the fully connected layers with 64 and 32 neurons. Both of these layers use the relay activation function. These two fully connected layers are followed by a single dropout layer with the rate of 0.2. The last layer in the network is a softmax layer with 10 neurons. This network is used in the learning step, regardless of whether the pipeline is trained using the deep learning or the federated learning. Here I present the results from the various experiments of the federated and deep learning models. Federated learning is an online learning strategy, but and on the other side, deep learning is an offline strategies. Together, deep learning and federated learning strategies were conducted to calculate 95% for this matrix of macro F score. This picture shows the macro F1 score. achieved on the test subset by the three deep learning models shown using dot lines, and three federated learning models shown using solid lines. These three models per learning paradigm differ only in the sensor placement that provide the data they processed. The horizontal axis shows the number of the rounds used to train the model, while the vertical axis shows the shift macro F1 score. This picture shows a clear ranking between the models that differ only in the sensor placement they use, regardless of whether deep learning or federated learning was used. For example, the worst performance was generated by deep learning and federated learning model that use the data from the wrist sensor placement, while significantly better results were produced by those using either the tight placement or combination of both sensor placement. In fact, the best DL and TEFL models were produced using the combination of both placement. The results show that all models tend to once the number of training rounds reach at 20. When comparing models based on their type, the result show that deep learning models always produce slightly better results across the whole range of training rounds. It is also evident that these models behaved very similarly and follow the same trend lines, with federated learning models taking a slightly larger number of rounds, achieve their best performance. Now this picture shows the confusion matrix of deep learning and federated learning for each activity class. Deep learning and federated learning exhibit very similar detection performance per each activity class. Both models achieve best performance for activities such as standing, lying, cycling, and running. But the worst performances are attended for shifts such as kneeling. However, it is also evident that there are specific activities where the deep learning and federated learning achieve better performance. For example, this is the activities such as walking and sitting. If federated learning achieves better performance compared to deep learning. This is very available result, and this is a very very available result, as it shows that the gain in overall performance of deep learning lies in the several specific activity instead of outperforming federated learning for each class. The next picture investigate the macro F1 score of different federated learning optimizers, FET Adagrad, the FET Yogi, and FET averaging optimizers, focusing only on the combination of both sensor placements. FET Adagrad and FET Yogi optimizers with the default initialization parameters, and the results show that the FET averaging provide the best performance in terms of convergence and macro F1 score. This optimizers is used for all remaining experiments. The emphasis here is performance analysis for federated learning based on human activity recognition from a system level perspective. The analysis also provides head-on comparison between two types of models, federated learning and deep learning. The results clearly show that the variety of system parameter and configuration, like the type of sensor placements, a federated learning optimizer, number of active lines per round, the model complexity, as well as can play the crucial role in the robustness and applicable of federated learning based on human activity recognition. Also the results clearly shows that the human activity recognition models trained using federated learning behave very similarly to the already wild used centralized deep learning model, and exhibit only a slight decrease in performance while being robust to parameter changes if appropriate number of rounds are being used. The future direction of research will continue to deepen the benefits and advantages of federated learning strategies in terms of creating different models that will have different domain and testing the behavior in relation of the deep learning. Thank you for attention.
So thank you very much, Borche, for your presentation. Now we have time to questions. Any questions to Borche?
Hi. Oh, there is one also in the chat. Can I ask a question?
Yes, of course.
Hi, Borche. It was a really good presentation. Yeah, I'm also quite familiar with this work with you because we're working together. But I would like to know, how do you see the continuation of this work? So I know that we discussed so many things, how to continue with this one, but what is the most promising one, if you can discuss a little bit in this forum?
Yes, I think that
including more data sets, or I don't know, trying
yes,
different deep
including
learning architectures.
yes, including the another data set, another methods, or another type of machine learning model, like split learning. This is very interesting type of learning, and I think that different models and testing the different models of this type of learning, we will see the behavior. What is the
different behaviors of the network.
Yes.
Yeah. Thank you.
Thank
I think there are two questions in the chat.
So the first question is, did you use any framework for federated learning simulation?
Yes, I'm talking about
So do you want to revisit that part and
yes.
Explain?
I think it was Flower, right?
Yes.
So we were using the Flower framework for this one.
Yes.
Okay.
Yes.
And we have one last question. How many epochs are in one round of federated learning algorithm?
50. 50 rounds. Yes.
Okay. So does anyone wants to make one more question? We still have time. Okay, if there is no more questions, I want to thank Borche again for the presentation, and remember that this seminar will be available on our YouTube channel, and you can revisit and contact Borche anytime if you have any questions. So thank you all for your presence here. Thank you again, Borche, and see you in our next seminar. Bye-bye. Thank you.
Goodbye.